All right, so now when we want to determine whether it is getting warmer or cooler over a period of time, we analyze data for trends. On this figure that you have right here, the average June high temperatures has been plotted for the Pullman Airport from 1940 until 2019 as a purple line. So you see there are some gaps in the data because those specific years weren't, or were ones where no data was recorded. Okay, the red dashed line that you have right here is superimposed on top of the purple line, and it is the trend line that shows the trend for the data. So basically this is the whole data, and this is just the trend that you are seeing throughout those nearly, what is that, nearly 80 years, right? Yeah, cool. So question number 7. On average, are Pullman June temperatures increasing, decreasing, or staying the same? So you can find that out based on the trend line itself. Do you see the trend line getting, warmer, getting colder, or staying about the same? Okay, so now comes a little bit of more mathy approach to things. So remember the basic equation for a line is y is equal to mx plus b. The slope of the line is m, and the y-axis intercept is b. The slope of the line indicates the change in y values over x values. The y-intercept indicates the values of y at the y-axis where x is 0. The equation of the trend line in this graph is equal to y equals 0.0168 times x plus 70.762, which means that, again, this is the slope itself, what is y with respect to x, basically, and then this is going to be the y-intercept. So from this trend line, which is, the equation for it is right here, this value right here is the b value, the y-intercept, and that is 70.762. This m value, again, is the slope. So using the slope, you can calculate the modeled average number of degrees warmer in June 2009, where it was compared to 1941. So that's what we're going to do. So calculate the increase in temperatures for June of 2009. Okay, how do we do this? First, we must input the degrees per year, meaning the slope. So here we're going to put 0.0168 times the number of years of data, meaning x. So in this case, we want from 1940 until 2009. So that is how many years? Hopefully you're thinking 69. All right, so you put 69. And you get a set number of, or a set amount of degrees that it was warmer in June in 2009 than it was in 1941. Okay, so that is just the amount of degrees that it was warmer, not the temperature. Okay. All right, so this type of calculation is a simple climate model. Climate models allow us to predict what climate might be like. We can use the entire equation to predict what the high temperature might be like. So in this case, we are actually using the whole equation for the high temperature, not just how many degrees warmer it was. So in this case, we're going to use again the slope, and in this case it's 1 year later, the slope times the number of years of data. So in this case, you're going to use 70 instead of 69. And then you're going to add the y-intercept, or that b value. So you're going to have a predicted temperature for June of 2009. All right, so then I tell you, the actual average June high temperature in Pullman in 2010 was 67 degrees Fahrenheit. And based on your calculation that you made here above, is that more or less than the predicted average that you had? So I'll let you think about these two questions later, based on whatever numbers you have and what you know so far about climate. All right, so now we move onward to part 2. Part 2, reconstructed climate with proxy records. So remember, proxy records are going to be some sort of record that we use from nature that has a way for us to not determine the specific temperature, but give it a range of values based on what we are looking at. So some proxy record might be things like tree rings. It could be things like coral rings. It could be things like ice cores. There's a bunch of things, as we have seen, especially in lecture, right? So I won't go into detail about the different proxy records, but we're going to use, in this case, for part 2, tree rings. So in the first part of the lab, you calculated a climate normal from observations made at weather stations. Again, those were actual temperatures that were recorded. In trying to reconstruct historic climate, we don't have observations for most locations prior to the 1900s, which is when we started taking those temperatures and were able to do so. So we have to find a proxy, which is a substitute that recorded the weather conditions in some other fashion. So one of the best proxy records available in climatology are tree rings. Tree growth is dependent upon temperature and upon precipitation. So tree rings that are wider or narrower depending upon the conditions for a given year will also tell us something about the precipitation and the temperature in that location. So since trees only normally add one ring per year, we can easily date trees to link the climate the climate conditions to the year where they occur. Okay, so this is an idea of what a core tree ring might be looking like. So you have a slice of a tree trunk, and then you take all the way from the middle of that tree trunk ring to the edge. A set number of years is going to be counted. So in this case, there's, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, about 14 or 15 years have been recording in this specific tree ring. And then based on the length and on the colors of them, basically, we can determine the precipitation and the temperature at that time when that specific tree ring formed. So another climate proxy often used are ice cores. These cores drilled thousands of meters into the ice caps of Greenland and of Antarctica gave climatologists a different and much longer scale view of how climate has changed and how the atmosphere has changed over time. So you'll explore some ice core sites in part 3 of this lab. Okay, so we won't deal with it just yet, but it's just another proxy record that we use. Okay, so in most of the western US, tree ring width is indicative of whether it was a wetter than normal year, a drier than normal year, or a precipitation normal year. In the example that we have below, 5 rings are highlighted. So in this case, there's a lot more than 5, as you can see, but by this little red arrows, if you would, lines, you can see that I have highlighted for you 5 specific rings, okay, from that tree core. So for each ring that is highlighted, use your ruler to measure the width of the ring in millimeters. Okay, so you need a ruler again here, and that ruler has to have millimeters, not just inches, okay? So make sure that when you are doing this, you are at 175% scale on the bottom right of the page, or the top right, aka assumed 175%. So as you're seeing here, I only have it at 100. If you print this out, it should be just as it's printed, but if you are doing this on your computer, go ahead and put it 100. Oh, see, it's not even there. At 175, okay, in order for you to get the appropriate numbers. So we will address the precipitation and wet, dry, normal columns below. Okay, so here, what you want to do is, for now, just place the width that you are measuring based on your recording with your ruler. So, tree ring number 1, and then you record whatever width that gives you. So in my case, as I am measuring with my ruler, I get a width, and you can do this on the top every time just to be consistent, or in the middle every time just to be consistent. It's up to you. This should be pretty much the same throughout the whole ring section. But when I'm measuring ring number 1 that is highlighted, I obtain about 16 millimeters of width. So that's the value that I'm going to input here in my table. You do the same thing for rings 2, 3, 4, and 5. As you see, number 2 is pretty wide, similar to 1, so is 4, but then 3 and 5 are both smaller, so the millimeters should be smaller as you input them here. Okay, so now that you're done measuring, we can go back to normal scale, if you would, and continue. So in some places where there have been weather stations for several decades, we can use tree ring data with weather station observations to determine the relationship between tree ring width and actual observed observation, or precipitation, sorry. So in areas where we have tree rings and also areas where we have actual weather stations, we can correlate between the two. So we can say maybe a wider ring might mean that there is more precipitation and higher temperature, or maybe it's the opposite, depending on where you're at. So again, that's based on the locations where we have both of those things. So on the graph that you have below, this graph right here, a relationship between precipitation and tree ring width has been plotted using known weather observations and tree rings for this location, so the location where this tree ring was obtained. Locate the measured width for each of your 5 rings to determine what the precipitation was for the associated ring. Determine if each of the 5 rings was a wet, dry, or normal year. So I'll help you with the first one, provided I already told you what the width that I measured was. So I said that the tree ring, number 1, I measured the width to be 16 millimeters, right? So based on this graph, we would say, okay, tree ring width is here measured on the x-axis, or is here on the x-axis, and precipitation is on the y-axis. All I know is that my tree ring width was about 16 millimeters. So if I were to follow this trend line, I see that 16 millimeters definitely falls within this wet years category, right? So I could continue it as straight as I could, and it would fall somewhere here, which if you plot that in the y-axis, my precipitation should be somewhere like 32 or 33 inches or something like that. So then when you complete your table, you would say, okay, tree ring number 1, because the width was 16 millimeters, will be a wet year, right, based on this graph. And then the precipitation in inches, I would say again somewhere about 32 or 33. So you could be exact and actually draw it out and tell me that based on your calculations. And then you do the same thing for the remaining 4 tree rings. So some of them might also be wet, some of them might be dry, some of them might be in that normal range, depending on the width that you obtain from the exercise of measuring them out with your ruler. Excellent. So once you have completed that table, you're good to go and answer the following questions. So question 13. The normal annual precipitation for this location is 17 inches per year. If a year occurred when the normal amount of precipitation actually fell, how wide would the tree ring be? So basically you answer this based on the graph that you have above. And you say, okay, 17 inches per year is the normal amount, right? So this is in the normal years, so 17, we could look exactly. So how wide would the tree ring be if it's corresponding to 17? So you would look straight across and onto the trend line, and I would say that it falls in about the 8 millimeter wide tree ring. So that's your answer for number 13. Pretty straightforward.